Hello, and thank you for joining me. You're here with data science teacher Brandon, and we're going to be discussing the random forest machine learning model today and kind of going through some of the features, some things to watch for, some things to really help you make it work better. And I think it's a really good model, and because it's a really good model, we really have to be concerned about overfitting to get the best predictions on our test set on new unseen. So let's get started. Importing the standard data science libraries, random forest classifier, standard scalar, and train test. Okay, we turn off the warning system. See that today? And I'm going to use uh, heart disease diagnosis prediction data set. Okay, so there's a classification of ones and zeros. Okay, so not really going to spend a lot of time on the pre-processing today. Not really the point today. I wanted to use a real data set though, because we just get a little bit more texture and stuff. So we can see as we're looking at the hyperparameters, we can get a better sense of what really would work. A little bit of treating the outliers here, clipping them, sides, treating the outliers, clipping, kind of getting rid of so nothing really causes a huge problem. I'm going to one hot encode the category features here, and now we have 22 columns. My train test split with my input features x and y here, x and y to train test split, x train, x test, y train, y test. Test size. Okay. So it's pretty standard workflow. I know I did that really fast, but really we're here to talk about the random forest, right? So not so much about pre-processing. Although super important, we're not here to really talk about that. Okay. So default hyperparameters, so just looking at what it is by default. So we're going to train a random forest classifier. We're going to fit it, just fitting it as I initialize it here with my train and my x train and y train. Define it as RF, random forest, score, score. So default setting score train, default setting score test. And so we'll kind of look and see, we'll keep these scores all collected and we'll see how it did at the end. Um, and keep that for surprise, and we'll save it for later. Yeah. So looking at n estimators, so let's go through and see. We go through a list of 5 to 500 different decision trees inside of a random forest by 5. So really looking at a very large percentage range of estimators. Train, score, train, and I'm going to keep track of these, and I'm going to go iterate through a list of that I created of the estimators right here. Fit each random forest for each estimator to append the train scores, test scores, and then plot, just a simple line plot for the train and test. Now, what's kind of nice about this is we'll be able to see the effect of our kind of step-by-step grid search, right? We're going to be testing all of these and see how it works, and we'll continue. I'll find what works well here, and then I'll continue using it, kind of adding to it. So it's manual, but it gives more, I feel like, direction to your grid search. It's kind of manual, but I think it provides a lot of insights and for in this class to really help us understand. Okay, so you can see here, I think the interesting thing, and as you play with random forest, you'll notice that more estimators don't equal a better score. You can see sometimes we got a really good score, close to 200 and stuff first round, but after that, we never got close to that again. We never really got worse. We started to taper off a little bit here, and you would eventually start to confuse your model with too many trees, but you will find that around 200 is a good, maybe generally larger amount to try. I would try 50 though, and that's a good thing to point out here. The best score comes from 50 right here. Okay, so it'd be something as well to try, um, because sometimes simple is better. Sometimes just throwing more math at the problem isn't really the solution. To be general enough to predict well on the test, it'd be simple. And random forest is so complex already with so many decision trees putting their accumulative vote together. It can be good not to use too many, especially on a simpler data set that we have today. So looking here, seeing a good score. So what I did is I took that and I got 15 estimators here and found this. We could, you could try this with a different data set. This would work the same and kind of show you how random forest. It won't always behave like this, but I have noticed this is fairly consistent with what I've seen in here. And so what we're trying here is the max depth. I'm noticing that max depth makes a huge, huge difference, and that's actually a really good important sign. Right here, we found that 3 is, or 4 kind of, this area is really the better size for max depth. You can see a good peak kind of right here in this range. I think the thing is about that is you really want your decision trees to be simple, and you want lots of simple, kind of weak learners. But as a group, they tend to predict better. We're kind of seeing that as we increase the complexity of our trees, it didn't instantly make them play with min sample splits, and we'll see a little bit, some other things that we can play with. But it is generally I've found that a smaller max depth will work well in a random forest. Not always in a decision tree, but in a random forest it tends to work. Min sample splits. What this is going to do is you're going to need to have a minimum amount of samples on a node to do a split, right? Or it just won't keep growing. So you'll kind of naturally allow one side of your tree to grow versus the other, and it can be kind of helpful. To look at this. Or to see, I feel like it's almost more max depth is going to say you're only going to grow to this level and then stop it, whereas min sample splits will let it grow one side of the tree. If there's enough data to support a split, it will continue to split to the max depth that we have here. And so I think it works really well here. It grows a little bit of growth, and you can see we did really well at train at first, but we got our best test scores kind of a little bit later, and we ended up using sample splits of 20. So we got really good on our test scores. Did better than our our train scores for most parts, and it's kind of just luck that's happening. Um, and we saw that as we're overfitting here, or as we reduce overfitting, we're getting a worse and worse score on our test score. It's interesting that's right above that's kind of just the balance. Min sample splits here. So min samples in a leaf, we need to have a min amount arriving at the next leaf. So this controls when they will do a split, and this will only do a split if each one of the landing, the nodes that finish the split have a certain amount of things. So it's going to do very much the same thing. It's going to kind of control the same thing in a different way. And so here I'm going to try the min sample leaves from 2 to 40 all the way up. See kind of right here. Getting a bigger number or getting that a smaller number is actually working here. So we get at least maybe 10, maybe 5. And here we decided on 13. So going again, you really don't need to have that many in sample leaves, but we want to make sure there's just a good amount of size. And so we're making it more general as we do this. And we're keeping, making more general as we reduce this amount. And so we're actually finding here it gets a better score here. I'm going through these. And you'll find, just to iterate this, you'll find this works a little bit different. So you're noticing I didn't choose the exact point on this graph this time. Last time it was the exact point that was the highest, and you won't get the exact point. It's kind of, because we're doing a random split, we don't know it will always be exactly the same. And so yeah, so with that, and then here max features. This is maybe my least favorite. This is one I almost don't normally play with. I wanted to show it here, and I actually didn't end up using my final build because it looks like it worked well here, but in practice I find it just always it doesn't work as well. So here we can see as we're increasing the amount of the max features used in our test score, so as a percentage of our total features of our 22 features, we're continually using more and more and more. So up here, max features, again, with all of my other hyperparameters that have been tuning, and we can see here, going to converge around a certain point. I would say 0.72 kind of made the most sense, but what I found is that really using all of the features was better. I've traditionally always found this has always been kind of something I want to see. You can see this plot. It says that really, if we used a low number of features, like 22, we probably get the best test score. It doesn't seem to really work in practice. Truthfully, you would make your trees as different as possible, but I don't find it works well. So, and you can play around with this. Test me, prove me wrong here. But I find that max features really is better just not to play around with. When you're building the one model build, it doesn't seem to ever work that well in practice. And that's just my personal experience here. And so here we're doing the scores of them. And so putting all of them together, we did the ones where we got the default scores and finally unveiling the default scores and our final scores. So on the defaults, we got perfect on the train score, very common with random forest, and 87 on the test. And we did all that. We reduced the train score down to 86. Right? We really reduced the overfitting. We got these two in alignment now. We got 80. We only increased this by a little bit. But I think you would say we built a much more robust model. We don't have any overfitting, and the risk of overfitting is crazy predictions. You don't really know where they're going to go. It's not just going to be the bad. Could crazy and really off and stuff. So you really have to be careful for this. So now we built a more robust model. Hopefully you understand how these parameters affect our random forest, and we can use the same workflow, for different data sets and data sets. I think you'll find lots of things that I say will be true for lots of data sets, but not always, right? So take everything that I said with a grain of salt and do your own experiments, set up your own tests. You now have a form how to do that. And I will see you for the next video.